All right, so welcome back. Welcome back. I hope you are doing good. In the last video, we have I think we have covered up transformer encoder in the last video. So in this video also we are going to cover up transformer decoder. I've already made a video on transformer decoder, but I haven't went to the depths. I haven't went to uh I think I haven't I just made a very small video and I didn't cover everything. I didn't cover the code fully in this video. I'm not going to code it like from now on because it is taking time. So I'm going to explain this line. I'm going to explain every line with the highest amount of context and highest amount of information that I can gather and the highest amount of intuition that I can deliver to you. So let's start. So first, yeah, this is transformer decoder. I've already in the last over the last video videos, over the last few videos, we talk about the transformer decoder, which is nothing but encoder, right? Sorry, my bad. So in let's say a language model, let's say we have some inputs and some outputs. So let's say this is a question, right? So this is the encoder. The encoder's job is to understand this question fully and make sure to provide some types of intuition and some types of information about this question, right? And it will find some information about this question. It will find some context to this question. It will find some mainly attention of this question, mainly which words are similar and all that. And after we have find these values, after we have done some things, after we have like some features are found, we are going to output some values which can be anything, right? And then we're going to send that to a decoder, right? We're going to send that to a decoder in which we are going to have an output embedding. I'll talk about this, right? In the inference time. So this is not the training, right? So this is not the training. When you are actually using, what is going to happen, I'm going to explain that. So let's say you give a question. Let's say what is 1 plus 2 or 1 plus 1. So let's say the question is 1 plus 1. What is 1 plus 1? So the encoder is going to understand this question, what it actually meant, and it is going to provide some context and some meaning. So let's say this encoder decoder model, this transformer is already trained. So remember, you can add as many encoders as you want, right? You can connect these encoders. The output of one encoder will be the input of another encoder. We'll update it to back propagation based on the derivatives of each encoders. So let's say we are going to have let's say a number of encoders. For now, let's say one encoder. Let's say this encoder is already trained. We have already trained it, right? So what is going to happen is we're going to provide some question. Let's say 1 plus 1. What is 1 plus 1? So what we're going to do is we're going to have a decoder. So at the start, we're going to have a start token. This token, this is token. This is not a word, right? So before the word, we are going to have the start token. So we are going to have this start token and we'll input the start token at the first. So and the decoder is going to do some operations. I've already told you what will happen in the encoder, and you might have some understanding of what happens in decoder if you have watched my video. So we are going to predict an output. Let's say the next word. Only we are going to take this start and we are going to predict the next word. Remember, this is not the training. This is just the inference time. We are going to predict the next word. Let's say answer. Let's say the answer. We are going to put that again. We are going to now in the last step we have only given the start token and then got the answer. Now we are going to give the two words, the start token and the answer. And then we're going to give answer and then we are going to predict the next word. And maybe the decoder takes that and predicts the word is. And then we'll give this two and predicts the model predicts two. Sorry for that. Model predicts two. So we have, and then after we've given two also, the model we want the models to predict the end token, right? And end token, which is nothing but which defines that the answer have ended. So that is a model, that is our ideal model. After training, of course, we want this type of model. And how are we going to do this? I'm going to do this. We are just going to cover step by step, and let's just go through the code first. Let's just study some. I think we'll go through some code. I think the only thing new for us is masked multi-attention. I'm going to cover that also very fastly. What is masked multi-attention? Why do we actually care? So let's say you're training the model. This is not the inference time. You're actually training the model. You actually know the inputs and the outputs. So while training, like if you should have most probably you should have known what is training, right? If you have if you have come this far to my videos, you should have known that we would while training stage we'll also have these inputs and outputs, what the model should take the input and what the model should predict. We'll have that. So in while training we'll have, let's say, many questions and answers, right? So many type of questions and many number of questions and many number of answers, right? We're going to have many questions and many answers. So we want our model to understand the relation between these questions and answers, and essentially, not just relations, some more complex features, and hopefully try to answer for new questions and understand the language most importantly, right? So that is our goal. So what we are going to do is, while training, so let's say you have the question as, what is your name? So let's say this is the question, what is your name? And let's say the answer is, as I've told you, while training, we'll also have the answers. We'll collect a lot of questions and answers, and the model will learn from them. So let's say the answer is, my name is Joel, or my name is Transformer. Now that we are talking about transformers, my name is Transformer. So let's say this is the required answer. We want the model to predict this answer. So what we are going to do is, right, so we are going to give this input and try to predict this output. So the why do we use mask encoding, mask multi-attention? Well, this is the thing. So let's say you have a decoder, right? And then I'm going to give it. So when you give this let's say when you give this sentence, when you give a matrix that contains the embeddings of all of these words, so each word is going to have an embedding. So let's say we have collected all of these word embeddings and input them in a sequential order, right? In some matrix, in some type of form. So what we are going to do is we are going to perform masked multi-attention, right? Multi-attention is nothing but finding the features of finding the attention of each words. So what we are going to do is, I've already explained all these topics, but I'm going to cover everything else. So let's say you have 3 words, right? So what we are going to do is, let's say this 1 to 3. So each represents words, let's say. So the first one, the number 1 represents the first word, 2 represents the second word, and 3 represents the third word. So what we are going to do is we are going to find the attention scores. 0.7. I'm putting anything. 0.8, 0.9, 0.5. Like you will have this course. So the diagonal is going to have a huge number of values, because the word 1 will have, like, the word 1 will of course be more similar to word 1. It's because both of these words are same. And then we're going to have word 1 and word 2. So most important things are how this word will attend to other words other than itself. So we are going to find how this word is going to attend to other words. So let's say that we are going to come to masked multi-attention now. I have gone out of topic. So if we come to masked multi-attention, we are going to have this sentence. We are going to have this sentence. So the why we do it is, let's say we calculate the query key value, but let's say we only care about we only have the my. So while training, let's say while training, we only have the we only have the answer as my. So we only have this. So let's say we only predicted this, or we only got the first word. So what we don't want to do is, we don't want to cheat, right? So we don't want the model to actually look at what is the second word. Like, that's common sense, right? So let's say I have this vector that contains all of these words. Any type, like any type of vector. You don't want the word when given the word my. We don't want the model to pay attention to the word name, because the model has not yet generated the word name. The model does not generate the word name, because in the training we already have the actual answer. We don't want the model to actually look at the answer. So that is the reason we apply masked multi-attention. That is the reason we do masked multi-attention. In masked multi-attention, we'll just clear all of these values. We'll just make all of these values as 0. Why we do it? Well, we don't want the model to actually look at the answer, right? So we don't want the model to actually give attention to the next word, which is not yet predicted, but on the training but while training, we actually know the answer, right? We don't want the model to actually, like when given the model should predict the word name. Rather than that, the model will actually look at this name and maybe cheat. So that is why we don't want to leak our data. We don't want the model even to have little influence. We don't want the model to even have little influence because of the second word, right? So even a little even the slightest of the influence because of this word will cause our model to actually not learn well. Because while training we actually know the answer, right? So that is why we perform mask multi-attention. That is just like very small theoretical topic that you should learn while learning transformer decoder. And remember, we only have that in decoder, right? We don't have to do that in encoder, because in the encoder we'll actually have the whole sentence, we'll actually have the whole question, and we can access the whole question, right? We are not going to predict the question. We are only going to predict the answer. So therefore we will not perform masking, because we want the model to actually predict, have attention on the next values also. So therefore we'll not perform an attention masking, but we'll only perform masking uh, for the answer while predicting the answer only in the training, because we don't know the answer when we're actually using it, right? The model doesn't know it, at least, right? So let's get to the code. And remember, I've referred you to this blog, amazing blog. He's a great I think a great person, Jay Alarmar. He also has also published some more papers and some more YouTube videos, which are quite informative and might be helpful for you, to actually understand new things. So in the first cell, we are going to get into the collab. I named it as new. I am named it as part 2, right? Oh, good. So wait a minute. I'm going to charge my laptop. I'm just going to pause it for this video. I'm going to. All right, I'm back. All right. So what are we discussing? Well, we have first covered this the first cell. We're going to get to the first cell. So what is the first cell? Well, nothing. We have just implemented the same things, the same libraries that we have imported in the last video, necessarily. Not last video, before that. So we have in this cell we have imported PyTorch, right, in order to build model, in order to do the modeling. We have imported math, I think, to do the square root here. And we have imported NN from Torch, use it to build neural networks. And we're also going to import functional from Torch. So just import this, and whenever you are using PyTorch, I highly recommend you import these libraries. It will help you, right? And then we are going to first do the classic scale dot product attention. What is scale dot product attention? I've told you earlier. We are going to calculate the QKV. We are going to have weight matrices, WK, WQ, WK, WV, and then we are going to multiply this weight matrices by a word embedding, and then we're going to get QKV values, query K value vectors for each word, and then we're going to multiply the query vector of each word with every other word, and then we'll multiply that V also by value vector of every word. By that we can actually understand how important does that particular word should pay for other words. So that is the main reason. That is the only thing we can find in scale dot product attention. Now I have actually added a new parameter, mask. I have set the default to none. So if when you are running the code, when you are using this code, right, if you don't want masking, right, if you don't want any mask, you can just leave anything. You don't have to specify any variable here or any matrix here. If you want mask, you could input a vector, but I have put mask equal to none. That if you don't input anything, if you don't type the parameter mask, I'm going to leave it as none. So it is going to consider it as none. So what we are going to do is same thing. We are going to calculate dk, again the dimension, right? And then we are going to calculate dk, and then we are going to do matrix multiplication between k and k dot transpose of -1 -2. I've already told in the last video why we transpose the k, why we shift the last two dimensions, because for matrix multiplication to happen. That is the reason we do it. I've explained that I have told why we do it in the last video. We're going to multiply by dk in order to add a normalization effect, and then we're going to do softmax to find probabilities, and then we are also going to multiply by v, the value vector of each word, right? And then if mask is not on, if the user specified a mask, or if the programmer that is using our let's say our decoder specifies a mark, or even us, right? If we specify a mask, we are going to add it. If not, we are going to not add any mask, and then we're going to return the attention. I have already covered this in the encoder section. We are just going to repeat that. And again, the feed forward layer, in which we are going to have demodel, hidden and dropout probability, and then we're going to have a linear layer. That's where we're going to build a deep learning neural network, or a neural network layer, a simple layer in which the input is demodel. We are going to have demodel inputs. Let's say demodel is here. Demodel is nothing but like I'm going to go there. So here demodel is nothing but let's say you have four. Let's say this is a query vector. Only the query vector. Let's say we have 4 values for the query vector. The size is 4. So what we are going to do is we are going to have, let's say, 2 heads. So it is nothing but query vector, size of query vector by number of heads by multiplied by number of words. So that is actually demodel. So if you think about query vector as 4 and 64, and number of heads as 8, and let's say the words as 200, then you can calculate it as something around, I think 8 fours are, yeah. I'm not very good at multiplications, especially I think 512, 64 into 8, 512, yeah, 512 into 200, which is somewhere around 1024. Yeah, 1000. Yeah, you understand, right? A lot of values. So we have yeah. So that is demodel. We're going to have that many number of outputs, right? So we are going to have 2 linear models, and yeah, we are going to have a dropout and ReLU, and then we're going to do layer normalization. Again, I've specified this in the last video. Nothing new. So we're going to have parameter shape, epsilon, gamma, beta. These are gamma, beta, and are parameters that are going to be updated, that are going to be optimized. So we're going to have this forward function, which will calculate the mean, will subtract the mean, and we'll calculate the mean, and we'll calculate the standard deviation. We'll subtract the mean and divide by the standard deviation in order to make this training more stable, right? I've already told you, because of the computational power, and to actually make the model. So if you don't do stable normalization, you might have the risk of letting your model into exploding gradients or vanishing gradients. So therefore, if we perform this normalization in order to make the make the values more closer to each other, right? I think that is it. And then yeah, so and then we are going to have multi-head attention. I have specified the shapes. of these outputs, just to make sure it is clear for you. Now, like for this, we are going to, for this example, let's say for this example notebook, for this example video, we're going to consider number of heads as 8, and the value of query vector for each head. The query vector dimension is going to be 64. Where the number of words we should predict at least is going to be 200. So that's it. So as you can see here, D model is going to be 512. Number of heads is equal to be 8, and the QKB layer, like multi-headed attention, you already learned that in the last video, but I'm going to repeat that again. So we're going to have QKB layer. So D model into 3. So we have only done D model is only for Q 512 elements. So we are going to do that for 3 because we have Q, K, and V, query key and value vectors. So we are going to multiply that by 3, 1536, and then we are going to have head dimension for each head. How many like what will be the dimension of Q? Probably 64 by 12 by 64. And then we're going to have the final linear layer after performing the attention. after calculating the attention. So we are going to have forward. The input for the forward. Again, we have asked added mask because we could like we are building a path flow of all these classes, right? So this path, this input is going to be propagated to all of these classes. So we are going to take the input from the multi-added attention and pass it to scale dot product attention. And further, we are also going to take the input, I think, from transformer decoder and pass it to multi-added attention. So again, here also I have specified the parameter mask, and then we set that to none. If no one, if no mask is added, no mask is specified, we are going to consider it as none, and we're going to pass this mask to scale dot product addition. So we are going to calculate the sequence length, the dimensionality, the embedding dimensionality, right? And then we are going to calculate the QKV, but from this layer, and then we're going to do reshaping. We'll reshape this into 200 by 8 by 192. 192 is nothing but the number of heads into head dimension, right? So the number of heads into head dimension. So the total number of no, it's not total number of values, but yeah. So we are going to reshape this into this 200 into 8 by into 192, and then we are to permute these values. We are going to change the positions 8 into 200 into 182, and then we're going to chunk it. We are going to divide this QKV into Q comma K comma V, and then we are going to send that to scale dot product attention, in which we'll calculate the attention vectors. So we'll actually get the attention matrix as the output, and then we are going to reshape this attention again into 200 into 512 matrix, a 200 into 512 matrix. So right, and then we are going to finally have a linear layer in which we are going to take this 512 and return the 512. So the output of multi-head attention model class will be 512 dimensional vector. I think, or a matrix, 200 into 512 dimensional matrix. Right, and then we're going to have this multi-head cross attention. So this is the new type of attention I'm talking about. So let me just open the transformer architecture photo. I'm just doing the blocks separately. The classic old architecture photo I've showed you. Right, hope we could see it. Right, so the encoder block part we have already talked about it. So positional encoding, you already know it. We in order to add positional data, so we're gonna have mask multi-head attention. Right, for QKV values, we are going to find in the question. So in the question, we are going to find like what word should give more importance to what word, and what word is more similar to what word. Both are same. So we are going to find that in mask multi-head attention, and then we're going to have add a normalization, and then we are going to have this cross multi-head attention, which I will describe now. So cross multi-head attention is nothing but, I'm going to go there. So what we are going to do is, let's just open the diagram again. Right, so yeah, so we are going to have this question, right? So what we are going to do is, we are going to have this answer that we have predicted, right? So so we are going to have this attention matrices, and so we're going to have this output from the previous multi-head attention. So what we are going to do is, for every vector we have predicted, we are going to perform an attention. We are going to perform an attention between all of the outputs from the previous encoder layer. So we're going to have some outputs from the previous encoder layer. If you think about it, I think the output is 512. Right, so I think the output is going to somewhere around 200 into 512. We are going to have this 200 into 512 dimensional output. So we are going to, what we are going to do is, we are going to perform attention between these two vectors. I'm going to say how. So we are going to have this output, which is nothing but 200 into 512 dimensional output. Right, so we're going to have this vector output. It's for each word we are going to have 512 dimensional vector. So what we are going to do is, we are going to perform attention. So QKV value vector. So we are going to multiply this. So this is the, let's say this is the question. Right, or the output of this multi-head attention after you have performed this multi-head attention. So let's say this is 512 boxes. So this is not 512 boxes, but imagine that this is these are 512 boxes, right? So that we are going to have 200 times of these boxes. So we're going to have 200 times these boxes. So what we are going to do is, for every word, each carries a number, by the way. So for every word, we're going to have 512 boxes, and then we're going to multiply these boxes by, let's say, WQ. We are going to multiply these vectors by WQ, and we're going to get Q vector, the query vector, right? And then in the question, right, we are going, for every word in the question, or not in the question, I'm going to, not in the question, but the outputs are also going to be, the outputs of this models are also going to be 200 into 512. Let's say we're going to have, we're going to have at least not 200. The input number of values in the input does not have to be equal to the number of outputs. So we are going to have some number of vectors representing each word, right? So, we're going to have some number of vectors, right? So let's some number of vectors into max sequence length, whatever selected there. So we are going to have some other again vectors. So what exactly we are doing is, we are going to get these outputs of these encoders. We're going to have some outputs of this encoder. So we're going to perform this attention. We're going to consider this as K, and we're going to multiply this by WQ, WK, and WV into WK, into WV, into WK, into WV. So we're going to multiply each vector by WK and WV. So thus we'll get K and V, the query and key values. Sorry for that. So we're going to have query and K values. So, and then we are going to perform the multi-head addition. So we are going to take this input, and then we are going to like multiply by K, and then we're going to perform softmax. We are going to divide by root dk, and we are going to multiply that by V. And yeah, so that is the thing. We'll do that again. We'll do this multi-head addition again. You could actually observe it. So just look at this again, the same old dimensions. But we are going to calculate K and V separately. So we're going to separate layers for KV and Q, because of the reason that I just showed you. So in the forward layer, we are not only having X, but we are also going to have Y. So here X is nothing but, in order to extract the KV layer from the question, so we are going to have this output from the question. It's some number of vectors for representing each word. Next, we're going to have some vectors that are calculated from each word. And then we're going to have these values, these vectors. And then we are going to form this KV layer. We're going to we're going to perform this KV layer on this vector. So we're going to form key and values. So we're going to have we are going to form key value pairs from this question, at least the outputs of this encoder. And then we are going to perform, and then we're going to get and then we are going to form queries from the from the decoder, from what we calculated here. So in the multi-head addition, we have changed these vectors, we have changed these embeddings into something that actually finds attention, gives at least finds which words are similar and which words are not, right? So we multi-head addition, in multi-head addition we'll added this pattern, and then we are going to find the attention between this question, the word, at least the representations in the question. We are going to find the attention between the representation in question and the representations in the answer. So therefore, as you can see here, we'll get the key and value vectors from the X layer, at least from the output of the encoder, and then we're going to get the query vector from the output of this multi-head addition of this decoder. In this previous decoder that we have, just look at it. And then we're going to do reshaping. I hope you understand what is going on here. Make sure to understand. So we are going to I'm going to draw it here. So we are going to have query key values. So query key values. Let's query is nothing but going to be nothing but output of the multi-head addition of the decoder layer. So we're going to have, let's see the output embeddings. Yeah, a little bit change output embeddings, right? Each word will have 512 words. So let's say this is 512 words. This is 512 yeah, a 512 dimensional vector. This is also 512 dimensional vector. So let's say there are 2 words in the question, and let's say there are 3 words in the answer. Sorry, this is the question. Sorry, this is the answer that we actually predicted, that we already predicted, right? So we are going to have these three questions, and then these two answers, and these two answers are not just answers. They are not just embeddings, but they are changed embeddings, right? So we are going to perform the multi-head addition on these vectors, and then we're going to get this output, and then we are going to perform multi-head cross-head addition after we have performed the multi-head addition. These are going to be the outputs of this encoder layer. So these are going to outputs of the encoder layer. So they are going to outputs of this complete encoder layer. So this is actually right, and then we're going to multi, and then we are going to perform attention. We're going to extract K and V. We're going to extract K and V. How can we extract K and V? We are just going to multiply them by some weights WK, WV, right? And then they are going to form key and value. And then we're going to multiply this, for example, this word by all of this K and Y. So we're going to perform, so we're going to multiply this Q by K, and then we're going to softmax and multiply that by V. We're going to again take this vector K, V, softmax, again take this vector K, V, softmax, and then we're going to do the same for this vector also with all of the other vectors in the answer, question. So that is the idea. You can actually see this idea working out. We're going to do that with X and also Y. We're going to extract KV from X. We're going to extract Q from Y. As you can understand, X is the question and Y is the answer of the decoder. I hope you understand. I hope you are comfortable with the terminology of question and answer. I'm using this terminology question and answer, not like may not be the right terms, but I'm just using this term. And then after that, we are reshaping it 200 into 8 into 128, and we are going to expand 200 into 8 into 64. Right? Yeah. So yeah, we are going to have Q. Sorry, Q is 200 into 8 into 64. To QA KV is equal to 200 into 8 into 128, because KV are like two vectors, and then we're going to permute them, both of them, and then we're going to divide KV into K comma V, right? And then we're going to perform scale dot product attention on QKV, and we're going to pass in the if upload and mask, right? And then we're going to have this, and then we're going to reshape the values, right, into 200 into 512, and perform the linear layer and return the output. So that is the multi-head cross attention. And then finally we're going to have this decoder layer. So decoder layer, we're going to combine all of these terms, all of this function, all of these classes that we have already coded, already built, I think. So we are going to have this init function, initialization function. Don't worry about this line. We are just going to initialize this class, and then we are going to call this multi-head attention function. As you can see, again, we are going to take these outputs, take these inputs again. We're going to take this XY decoder mask inputs also. So we are going to have this. We're going to initialize all of these classes. Norm1, drop1, encoder decoder attention, multi-head cross attention, norm2, dropout2, feed forward neural network, normalization 3 layer, and dropout 3 layer, third dropout layer, sorry. And then we are going to have the ResNet combined architecture as we have shared. And then as you can see here in the forward layer, we're going to take in X, Y, and decoder mask, right? So mask can be specified if you want to, if you want to use this class, right? If you want to use this class, you can specify mask, and then we're going to calculate ResNet Y to actually store this value and add it again. So res Y equals Y equals we'll perform self attention, dropout. I think self attention is nothing but multi-head attention. And then we're going to drop out normalization and add and normalize. Again, we're going to store it. We're going to do encoder decoder attention, which is multi-head cross attention, which is if you look at this figure, we are exactly doing whatever is in this figure. We're going to perform the mask multi-head attention. We're going to add a normalization. We're going to perform cross multi-head attention. That is exactly what we have done here also. We have to drop out normalization again, do that again, feed forward neural drop out normalization. And then finally, we're going to return Y. So finally, sequential decoder. I think we're just we're just looping through all of this. Yeah. So yeah, we are just covering the whole function. right? Remember, that is the reason, right? So we can have as many encoders and as many decoders as possible. That is the thing I have shared earlier. So let's say you want to add four encoders. If you want to add more complexity, if you want to build something like ChatGPT, let's say tomorrow. So if you want to add more complexity, more if you are solving more harder problems, and if you are if you are solving more harder problems, if you want more sophisticated language model, you could add as many encoders as you want and as many decoders as you want. So the output of one encoder is going to be the input of the next encoder. In the same way, the output of one decoder is going to be the input of the next decoder, and then we're going to multiply that all that, and then we're going to optimize all of them by back propagation. Don't worry about that. And then yeah, that is the thing we have shared here. We don't have the number of layers also as an input. The default is 1. We have set the default. If you never don't set the number of layers, we'll consider the default is 1. And if you could specify a number of layer, and we're going to have that many number of decoders layers. And then in the forward layer, we're just going to loop through in all of these layers. So that is the that is a like decoder program. So I think I can cover up decoder transformer architecture from this to like after this video. We can cover up transformer architecture in probably in the next videos. We'll probably try to code them up, maybe try to build some I don't know text summarizer, or question answering chatbots or translators. We'll try to build something that is maybe useful, something that are maybe fun, so let's say for maybe we'll try building chat gpt, or maybe we'll try building all, right? Maybe in the next video I will do text summarization, maybe in tensorflow. I'm going to plan all for that. So thank you for watching this video. Hope you understand that. And I thank you for watching, and I'll see you in the next video.